Hi everyone, this is going to be a video about triple integrals in spherical coordinate system or spherical coordinates. The textbook usually introduces this part very nicely. I just wanted to add a little bit more of a clarification on here and there. So that's the main reason why you usually find this content in the textbook. So let's review the spherical coordinate system. It's not introduction to the spherical coordinate system, I assume you've seen it, but here let me emphasize it in a slightly different way if you didn't approach it this way. In the spherical coordinate system, I think the most important thing is that you recognize this cone. This cone serves an important part. Many of you at this point are familiar with polar coordinate system, so to enter spherical coordinate system, the important part is recognizing this cone. So I have a point B here. So if you create a ray or line segment from the OB and then triangle this OAB, which is right triangle and right angle up there, and by rotating this around the Z, it creates this cone. And this cone, if you look at, for example, B prime, OB prime, you can imagine this OB prime has the same angle as this right triangle OAB prime and OAB is a congruent right triangle. Therefore, angle down there and angle down there, if you look at OAB prime, they're going to be the same. So let me show you the picture. So this is a picture. If you look at OAB, that triangle, it's copied here so that you can easily see that triangle, and OAB prime, that triangle over there, is a congruent triangle. The top is a circle, therefore AB and AB prime the same length and 90 degree, and OA is a common, so that makes these two things equal. So that if we call that OB rho, it's a Greek letter O, rho and rho, then this OA is common, and that's exactly the z coordinate of the point B. So z coordinate is related with this rho, the length of this position vector OB, times this angle that is forming with the z-axis, positive, especially the positive z-axis. So that's two pieces that is involved in the spherical coordinate system. So the cone is really easy to recognize all the points where the this angle, phi angle, is all the same. So that will be the locus. If you extend this cone to infinity, that's a collection of all points for which the phi value, the phi angle, is the same. So that connects rho with this phi value to the z coordinate. So what about x and y coordinate when we're going to look at this projection C? So if you project down to C, and that's going to tell us what the x and y coordinate is. So we're going to look at this triangle where OCB is 90 degree. So here's how this OCB look like. That triangle right there, OCB, and the angle, and that rho is indicating this length, OB is rho. That angle down there with the double arc line, that's phi. So therefore, angle across here must be phi, and A is over there forming this rectangle. Therefore, down there is across an opposite side of this angle phi, therefore must be rho sine phi. So that's OC. So think about what this OC is. After you project this one down, that's the x, you preserve the x and y coordinate of point B. Now, getting the polar coordinate is the idea here. The C is now in xy plane. OC serves as the radius r. Now I'm showing you the whole thing, which is the following. This OC here is this part here, OC on xy plane, and this r, which is figured out here, OC, in terms of rho and phi, r was this rho times sine phi, but once you have this r is a polar coordinate, so there you see x and y and r cosine theta, r sine theta. Now simply replacing this r, we have this version where it involves rho, the position length of the position vector in the three-dimensional space, and phi, here's the angle that is forming with a positive z-axis, and theta is when you project it down to xy plane, that usual polar coordinates. So these are called the spherical coordinate system. Although it's not too complicated, it really takes time to get used to this spherical coordinate kind of cube they call the spherical wedge. But let's take a look at the example. So I forgot to show you this important part, the qualitative description of what we were just doing. All the points x and y and z in this three-dimensional space has this rho value and theta value and phi value assigned. Most of the time this is one-to-one correspondence, except as a 0 is a 0, there's a unique value assigned to it. There's no two other points that are non-zero have a same triple information here, pieces of information, rho and theta and phi. They're pretty much one-to-one correspondence outside the 0, 0, 0. For example, let's think about all the collection where rho is 2. The length from the origin is 2. That's obviously the sphere. So this sphere has a complicated Cartesian equation, but in a spherical coordinate system, that has a simple equation. Rho equals 2. For example, r equals 2 was a circle in a polar coordinate. Okay, another example is theta equals pi over 4. So theta is the polar coordinate, so it's all about xy. Whatever that happens in xy plane, then you create the cylinder along the z-axis. That's what this is. So you know that's a straight line in xy plane, theta equals pi over 4. So that will be the plane. It's not straight line. The better way word is a ray. Starts from the origin here and going to this infinite of this first quadrant of xy plane. Then you can make it a plane out of it vertically. So that's what this collection of all points where the theta equals pi over 4. So here's a phi value. I've already given you the description of what happened if I fix phi, and so that's a cone. So we want you to go back and review if you don't remember, but that's what it was. And especially I made it into a dotted part, so indicating that this is not a truncated cone. This cone goes to infinity. Any points up there that any here and there, I was outside this window, any points that are here, and that the phi value, the angle here, it's going to be pi over 4. And it's also interesting, if this phi is pi over 2, then it's going to be over here, making this xy plane. If it is more than pi over 2, it goes beyond this plane as kind of opposite side of a cone or something. Well, this time let's take a look at the range. So there's no condition on phi or theta, but only there's this condition on rho value. Rho must be in between 1 and 2. So if it is 2, that's going to be this outside sphere. If it is 1, it's going to be that inside sphere. So it's in between. That's what this is going to be. So there's a hollow inside and some stuff in between these two surfaces. That's what it is. Okay, let's look at the theta value. I was wrong about this. Is pi over 6 and this is pi over 3. So that will be this 2 angle. Again, this is all about xy plane. This theta is just about xy coordinate. Therefore, if we have something in between these 2 angles, we know that's this ray in between, and then you have to extend this one along the z-axis. So it's going to be, this shape. Of course, it's infinite. And recognizing this shape as a wedge is the important part. So let me emphasize another part here, that phi equals pi over 4 earlier there, like this one, phi equals pi over 4. This is a cone, and this theta equals in between. That creates this solid, which is a wedge shape. So this is important part. That's why we're calling the region we're about to sketch is a spherical wedge. So here's about the phi value. It's phi value between something, and that's going to be that angle right there outside must be pi over 3. Inside angle must be pi over 6. So we don't include that inside part of the cone, but in between that cone, that's going to be this solid we're talking described in here by this inequality. Finally, I'd like to add one more about the phis. Phi is not quite the rotation. Don't look at the phi as a rotating or something because of the shape. Phi is rather, kind of rotating away from the z-axis, and it is kind of weird rotation. So, for example, if you think about these two angles, more than pi over 2, then it's going to be something in between. But if it is from 0, for example, 0 to 2 pi over 3, that's going to be kind of everything that is included except that this cone or something. So that you need to practice more with this phi part to get used to it. But that's roughly regions that has condition on those three spherical coordinates. So those were the surfaces, or not the surface, the solid, where the one variable is ranging. Now we're looking at all the three coordinates, spherical coordinates, rho, theta, and phi. They all have a lot of limits around. Let's see how they're going to form, what kind of solid they're going to form. So for example, here rho, the radius of a sphere, varies from 1/2 to 1, and theta varies from 0 to pi over 4, and phi varies from 0 to pi over 2. Okay, so let's remember that part. So here's the picture of that situation. Let me remind you, the rho varies from 1/2 to 1. So this is the z-axis, and that's the y-axis, and behind all that, there's x-axis going across like that. So I didn't make it dark, it's just all the behind everything is happening here. So let's look at the rho. Rho was 1/2 to 1. So here again, rho was 1/2 to 1. And in this picture, rho is the distance from the origin right here. So if you look at this line, a particular line, that is corresponding to theta equals pi over 4, that's one of the value in there. So if you look at here, it's clearly, okay, if this is 1/2, that must be 1, because it seems like a 2 twice. So those are the 2 points where clearly you see the rho varies in that way. And then you should think about the region, the range of rho that was in between the two spheres. So that's why it looks something like this. So the best way to start, I think, is this theta value, the wedge. That the term, this one is called, the reason this one is called a spherical wedge is because of this theta value. So let me show you what the theta value was. So here's the theta value. Theta varies from 0 to pi over 4. So that's why if theta equals 0 will be this x-axis itself, and theta equals pi over 4 will be this slope 1, line of slope 1 in the xy plane. So everything, the solid must be contained within these two wall. That you can imagine there's this wall, and then whatever the solid we have should be cut out by this. And phi value is in between 0 and pi over 2. That means the phi equals 0 is the z-axis, and pi over 2 will be this entire xy plane. If phi was from 0 to pi over 4, it would be more trickier because we have to cut out using this cone, right? Remember that theta value, phi values, given phi values, we have to play with the cone, but when phi is pi over 2, it's a bit convenient. This entire upper half plane has this phi value pi over 2. Think about this cone is wide enough and become almost flat. So if you have to sketch this one yourself, like I said, first I'm going to sketch this theta value down there. And whatever the phi value is, I would go ahead and sketch from the xy plane. There's a theta line in there, and mark what the rho values are, and begin to sketch the circle from the largest rho value and from the smallest rho value. So draw a theta line and mark this upper limit and lower limit of the rho value, and begin to draw a circle that is going toward to the z-axis. That's how this phi varies. So you roughly sketch it like this. So if phi is requiring between 0 and pi over 2, you're going to only take this portion of the line, that portion of the line. If it is saying pi over 4, that would be the pi over 4 right in the middle here, pi over 4 phi value, pi over 4 to pi over 2, that you will take just this portion of the line, stuff like that. So disregard phi for them at the moment, sketch this theta line, and draw these rows, two values of the row, and get this full wedge all around from 0 to pi, and then try to cut phi value at the end, and you will a reasonable amount of effort, and you will arrive at here. So this is called spherical wedge, where this phi and theta and rho and theta and phi vary freely, and with this upper and lower limits, that it looks like this typical shape. Next thing we're going to do, the whole main reason I'm making this video is being careful about what is happening down here and up there. That's pretty much the reason I'm doing this, making this video, doing it a little bit more specific, and be careful. Not too much. It's very sloppy still. So what I'm going to do is that we're approaching the Riemann sum, so we're going to divide this rho part and theta part and the phi part. So if you divide, so if this is the E, then we're going to divide the rho, and then small piece is going to call delta rho, of course. And if you divide this angle theta, you're going to call it delta theta. And then along this phi direction, if you divide it, you can see there's 1, 2, 3, 4, 5, the red part, that those are the phi lines where the phi value are equal. So those are going to be the division. That will be delta phi, which I forgot to write down here. So those three divisions will create this type of cells. So I'm calling the sample 1. We're going to sample 1 and below, and I'm assuming it's important to make this exaggerated. Let's say this kind of in this part down there, the sample 1 is the very bottom pieces. The length of kind of the magnitude of delta theta and magnitude of delta rho and magnitude of delta phi, they're approximately the same. So if you take that out, and because it's the radius 1 there, this size and that size is pretty much the same. That's what I'm trying to say. So it's all the sizes are very similar length. So that the next sample we're going to choose is a sample that is very close to actually z-axis right there. So we're going to choose this sample, and that we're going to call sample 2. So little cube-looking piece down there, and a little cube-looking piece down there, up there, all right? So here's a sketch of sample 1. I go down there and then take that piece out, and then the side part was definitely delta rho. That's the, if you go there, and theta is fixed and rho is changing, so that is exactly delta rho piece. And this side here, it seems like correspond to that side right there. So if you look at the bottom circular sector, and if you happen to be in general, you're going to be in some way in location rho k. This is your rho all the way up to here, the location. This length here is rho k. Delta rho is just a tiny piece. So rho k times the angle delta theta will be the circular arc. So the length of that circular arc is rho k times delta theta. The reason I put this squiggly rho is that the sample 1 squiggly equal symbol, approximation symbol, the sample 1 wasn't, at the time I was thinking, wasn't exactly the bottom part there. It was just like something sample that is relatively closer to the bottom piece. But if it is exactly bottom piece, this will be exactly equal to that whatever the rho n, the last piece there in there. So that's a good approximation anyway. So let's think about this side here. That side came from kind of this value here. Think about this value right there. That came from how you divided this, this phi angle. Phi varies like this. It's kind of vertically toward to the positive z-axis. So that's how much it's. So you can see all around these pieces, this is exactly theta phi and theta delta phi and delta phi and delta phi and all the same. So that's going to be exactly delta phi times rho k, or whatever your radius is. If it is outmost radius, it's going to be rho n. Inside somewhere is going to be rho k, and all the way inside, that's going to be rho 1, something like that. All right? So the whole deal is that comparing this equal symbol versus this exact symbol there is just all around in this division, the way we divided this spherical wedge, the delta phi is all the same. Okay? And it seems like this delta theta is changing, and that's the whole point of this one. Or while delta phi is all the same, this delta theta, which is just constructed in the xy plane, and as we put this thing above there, they're all squeezed in to the z-axis. So this length of this one is dramatically changing. Doesn't matter how small this delta theta is, there's a significant proportional difference in this length down there, and follow the line and the top length up there. So let's look at the sample 2. Here's my attempt to sketch some of the pieces up there. All right, this side piece, as you can see, is because it's cut out, this horizontal red line is cut out from cone. This is where exactly phi value is equal, and then you can see they're always equal. Doesn't matter down there and up there, the delta phi value, delta phi value is always equal. So if you look at the outmost part, that's going to be rho n times delta phi. So it's same size as the bottom there. And delta rho is going to be the same. You can see that we divided exactly, keeping the rho in there. But again, this horizontal line here and there came from the phi line, and the only time that we divided this theta part is down there, and they're somewhat being squeezed in up there. So it's definitely up there is very, very small. Right? So down here it's longer. In this picture, if you believe this picture is fairly correct, you can see that's up there, the length, and if you follow this line where all this theta value is fixed, right? Doesn't mean this angle here is a theta. If you project it down, if you remember how we define the theta of a point xyz, we project it down, right? So that's the same theta line there. But if you can see, the length is a lot smaller. So this piece will have this horizontal length right there is relatively a lot smaller. If you go all the way up there, a lot smaller than side length rho, delta rho, and this part where we start, I assume, or pretty much equal sides in here. Then if you pick up some sample over there, it's not. So the whole point is that when we estimate the volume of this one, if there's some significant proportional difference is going on, and up there and down there, it should be reflected. So again, this is very sloppy way of looking at it. Once this works, and then we can kind of provide the reasoning, but it never constitutes a good proof. So proof requires a whole lot of different approach. But so we see the problem, so we have to be careful about that part, the horizontal part and outside the surface. So we try to kind of estimate that nicely. So this picture kind of gives a contrast and how different this could be. So this is the bottom part. I chose phi value is closer to pi over 2. So you can see this red line here is this phi line where phi is fixed. And you can see that's close to pi over 2, starting from here to there. But this b prime, O to b prime, is kind of closer to 0. So the phi value is going to be like this. And these two rays are the theta lines, where this is some theta value, and it's just the difference between these two is supposed to be delta theta. And here is certain size, because as we make this line, keeping this theta value equal and changing this phi value, and it has to go to this z-axis, and because of this wedge shape of this theta value makes these two things squeeze in, so this is going to be closer and closer together as you go up. So it depends on what the phi value is. Down here, wider, up there, it's closer. It depends on what your phi value is. In the picture, you might think that down there, it's all the way bottom, that's the delta theta, difference of delta theta. Isn't this angle and that angle all the same in a delta theta? If it is directly perpendicular up there, somehow we can make sense out of that. If you can make this exactly rotated, this arc down there, all the way bottom in here, that circular sector is perfectly rotated around some sort of axis here, but that's not really the rotation. Here we're looking at, they're getting closer and closer to each other. So theta, delta theta down there, this, if you look at this OAB sector here, the computed here, that's because it's slightly higher. It's not really the angle is delta theta, but since it's closer to the bottom, it is kind of closer to delta theta. But if you look at it here, we have exactly the same radius. This is, let's say that's a row and that's a row. So we are looking at the same radius row and row, but the circular arc here is clearly smaller. Therefore, that cannot be the same delta theta. It should be a lot smaller than delta theta. So we need to get the good measure of that. If you know what this angle theta, this angle difference is, then you can easily calculate that. But at this point, it doesn't seem like it's easy to compute what this angle theta is. So we have a slightly different approach. So here's the idea from the book, is that if you project this point B prime all the way down to xy plane, and this A prime to all the way down to xy plane, then they think this the circular arc, if you change that to the straight line down there, they think it's a good approximation. Okay, so we're going to think about the projection. Yet this circular arc, and you see here, and this ray R2 and this axis z-axis, they're all making this a one plane. So this perpendicular projection onto xy plane will land on this R2. So that's why you see over here that O and B prime is sketched here, and Z, by definition, that's exactly some phi value, and we're projecting onto the xy plane. That'll land on exactly R2. So R2 here, I'm going to call that a B double prime. So what is the length of this one? If we know this length, which it will be this length here, somewhere about that. If we know that one, because at the bottom we know this angle is a delta theta, right? So we can use that all the way at the bottom. So let's calculate this side here that corresponded here. So because of the phi j and phi j, that's a rho k sine phi j, because it's opposite sign, and this radius right there, this length O to B prime, is still rho value. So that's the down there. It has the sine phi factor. So this picture here is after you project this B prime all the way down to B double prime, the point will land in here, and another point A double prime, if I say. So this is a picture on xy plane where this R2 and R1 rays are copied down here, and all the way to the end there's this point right underneath that B and A. Those are these 2 points. So their radius is a rho k, but what it land on here is it could be far small like this. So that's the B double prime and A double prime. And the length of this one is exactly that part right there, and that's how it's calculated here. So that's rho k sine phi j. Again, in the bottom, these 2 rays, we know this angle is exactly delta theta. So we know how to calculate this one, and we think this is a good approximation of this part here. This part came from the circular arc of this rho k, but this one came from the circular arc of a small k. So this is not quite the same circular arc, but it's approximately good enough for the integrals, triple integrals we're about to do. So those are the part that you have to be careful and correctly argue, but here we're just trying to explain the formula and try to make sense out of it. Okay, so we calculated that this length, AB prime, as this radius times the subtended angle in there. So let me show you the formula there. So I copied everything and sketched it again. So there's a B prime and A prime. They're projected down to B double prime and A double prime. That length is not congruent copy of this one. Slightly different curvature, but this approximation is good enough. And there is this picture again. So this arc length of A double prime, B double prime is the radius times the subtended angle, which is still delta theta. All right. So we got that nice approximation of that part, which depends a lot on the phi value. Phi value here is smaller, and phi value down there is almost pi over 2, right? So let's look at that little tiny piece, sample 2 especially. Okay, here's that sample. Again, because of the way we divided the cell, this rho k, the delta rho, is always the same, no matter which piece you look at. It's delta rho is always the same, and also this rho k delta phi is not quite changing as we change this phi value. The whole point is it's changing the phi value. It has this rho effect. So if the rho is different, this will be slightly different. If it's away from the origin, this is going to be a lot longer than if we're looking at this type of cell closer to the origin, then this will be very small. You can imagine that by extending this line, something like this. So that part depends on rho k. This is something we saw in the polar coordinates, so didn't make a big deal out of it. This is slightly different. That's why we're focusing on. So if you're closer to the theta equals 0, and that's reflected right here, sine phi, not theta equals 0, sorry, just keep mixing this theta and phi. This is phi, so if phi is very small, sine phi is going to be very small. So that's coming into the factor there, okay? Just rho k sine phi is this multiplicative factor to this side here. If it is all the way down there, which is phi equals pi over 2, so you can see phi pi over 2 here, sine phi pi over 2 is 1. So that just picks up our original estimation all the way at the bottom, but as we go up, there is this additional multiplicative factor, sine phi kicks in. So we got a good estimate of each of the side, and knowing that these are very, very small pieces, maybe we can assume this is pretty much the rectangular box, so that the volume is just multiplying these three quantities as is written here. So the volume of this one is a product of these three quantities, which are all, except this one, which are all kind of estimates. So this is a good estimate. So the rest of the part is just go back to the Riemann Sum and switching things around, and from there it's the familiar business. All right, this whole thing is about change the variable of a triple integral. The triple integral is usually interpreted as a mass of a given solid. So here's the density and multiply by the volume, and of course is all the XYZ coordinate will change this spherical coordinate system, which is this one. X is going to be rho sine phi times cosine theta, and y equals phi sine rho sine phi and sine theta, and so on. So our deal is rewriting this volume v in terms of delta rho, delta theta, and delta phi, and there is some adjusting factor, stretch factor, namely the Jacobian is involved, and we figured out Jacobian is this rho squared times sine phi. So now let me show you the whole thing. So this x and y and z is replaced by this rho sine phi and cosine theta. That whole thing is the x value, and I didn't repeat the rest of the part. It's just spherical coordinate system, and this delta v is replaced by our good estimate, right? So that's not exactly equal. That should be a squiggly symbol. So that's an estimate. And as we divide it finer and finer, that's supposed to approach the triple integral, that's the definition of a triple integral, and using Fubini's theorem, we can turn that into this iterated integral where all this thing just turn to normal variable, rho and sine phi. So that's the formula. F, the density is there, and we're switching dx, dy, dz into d phi, d theta, d rho, and with this stretch factor called Jacobian, which is in spherical coordinate system, this rho square sine phi. Polar system, there was just simply r, and this time is rho squared rho squared sine phi is the factor. So like the polar coordinate system was a good example of a change of variable for double integral, this spherical coordinate system is an excellent example for the change of variable of a triple integral of a three variable. So here's I've already set the Jacobian factor for three variables. So let's look at in the general picture. Suppose we have this weird shape of a solid we're looking at, or something that is inconvenient for XYZ coordinate system, and especially for the triple integral, it's difficult to integrate. Is there a way to reparameterize it such that this STU, as STU varies, this covers all the x, y, and z involved, not only on the surface, all the way inside the three-dimensional shape, while these S and T and U are varying freely. From S is not varying, not depending on T and U, T is varying, not depending on S and U is varying, not depending on S and T. So if you go to the space of S and T and U, they're varying independently, that will be exactly this rectangular box. So if you can rewrite the Riemann sum of this thing, that is in terms of x and y and z, if we can rewrite it in terms of S and T and U, the integral limits will be just absolute constants, and then you've seen that whenever you have integral limits absolute constants, the computation is sometimes really nice, just like passing through each other and quickly becomes one variable integral and product to each other, something like that. So that's the main goal. If this happens, if we realize that this weird object can be straightened out by this parameterization, then what's going to happen? How are we going to calculate this integral? What is the Jacobian factor, right? So let me show you this picture. It's very, very similar to polar coordinate system, and nothing is being proved here. It's all claimed and kind of explained. So it's actually a lot of calculation to justify whatever we're about to say. So we have this transformation. X and y and z are functions of S and T and U. So suppose I take out a little sample from that nice rectangular box, and this is very tiny rectangular box, and there's some base points there. That point under that transformation goes exactly to that. Now this entire thing is describing how this three-dimensional shape is stretched and bent to this three-dimensional shape, but let's think about just this line right there. Let's say that's where T is varying, this is S is varying. All these edges here, and the other two variables is fixed and one variable is changing. They all correspond to these edges of this accelerated jello shape, If you just focus on that line right there and compare with that line, and the derivative of this one as S varies, for example, what's going to be, derivative of that? That's exactly the velocity vector of that line. This line goes to that line. If you differentiate with respect to that line, that's going to be the velocity vector. So we have a position vector x, y, z, and one of this velocity vector is differentiation with respect to one variable, while the other two is fixed. So if you look at the vertical, that's definitely u is varying, for example. So all the other two variables is fixed. So this is kind of this line, if you just focus on this line here, is mapped to this squiggly line, and this velocity vector is exactly the differentiation with respect to the corresponding variable, like u here. So if you look at this three sides coming out of this base point, then we have three velocity vectors at that point. These velocity vectors are actually huge relative to the size of delta u and delta t, so that's why I draw like this. This is supposed to be very tiny, bent parallelepiped, stretched and bent parallelepiped, and this velocity vector is actually huge, right? So, but this is kind of showing the right shape and right size along the way. So if you just, there's a right amount of scalar factor there, and which can be justified, using, can be discovered using the mean value theorem and stuff. Turns out, right scaling factor is delta S. Delta S is a small number, so if you multiply the delta S, it's going to shrink. If you multiply delta T, it's going to, this part here is going to shrink. Multiply delta U, that part is going to shrink, and so on. So after you shrink by exactly this factor, it kind of fits perfectly in the sense of approximation. Right, I forgot to explain something. So once you shrink this one, and how we're going to compute the volume of the parallelepiped made out of the shrunk three vectors, remember that was exactly the determinant of these three-dimensional vectors. So here's the determinant. So here's the volume of the tiny piece, the determinant of the three vectors, which were this velocity vector scaled down to by this vector delta S and delta T and delta U, right, as a column vectors. The property of the determinant map is that if you have a common factor of a column, that factored out, and if there's a common factor of another column, that factored out again. It's multilinear. And delta U will factor it out. So you will see all product of this delta S and delta T and delta U outside, keeping this clean three velocity vector inside the determinant. So then it's going to look like this. I did it in the wrong order. So, and after you factor that, common factors, scalar factors out, and they're going to be outside right there as a positive quantity, and what's left inside is just a clean determinant value, right? So this factor multiplied to the volume of that tiny piece that we showed earlier, right? There's this tiny piece. The volume of this one is delta S times delta T times delta U, right? So that's the volume that we're about to integrate along, but there got to be this stretch factor to match the volume of delta V correctly. So that must be the Jacobian, and that's the definition of the Jacobian of three variable parameterized along another three variable, and that's the Jacobian. It's quite similar. If you look at just 2 by 2 box right there, that's exactly Jacobian of a 2 by 2 case, right? So here's the formula, the integral, the triple integral, and with this difficult shape, inconvenient for x, y, z, the Cartesian coordinates, then we can change the variable x, y, z if you have nice parameterization, and if that change of variable allows this rectangle the integral with this absolute constants like this, and then you change each of the variable with this s and t and u, and change the entire integral in terms of s and t and u with this adjusting factor Jacobian. It's determinant. So last thing we will do here is just an example you probably already know about this connection. The main motivation was to look at this effect of phi to the volume part, but here, and since we switched to this general change of variable, let's apply that idea of the change of variable to this spherical coordinate system. Okay, so again, x is r cosine theta and r sine theta, but that r is not exactly rho. Rho is a three-dimensional line, and r down there is radius for the xy plane. So you project that rho down, and that this is what happened. If you project that rho down to xy plane, this rho sine phi is the size, and rho cosine phi is the z coordinate. So if you differentiate this one with respect to rho first, and theta and the second, and phi and the last value, and fill in this 3 by 3 matrix, and that's going to be the Jacobian. So here it's what it is. Or here it is. It's written vertically, so you copy down exactly like this, because differentiating with respect to rho is going to be just all one. The second variable here is theta, so there's a theta here. So if you differentiate with respect to theta, you can see there's no theta here, so that's why you see 0. And theta there will be negative sine and positive cosine. Third one is along with the phi, so if you calculate with the phi, cosine phi, So this is wrong. It's supposed to be cosine phi. Sorry about that. Alright, I think I fixed it. I wrote over, I copied and pasted, so that should be cosine phi and sine theta. And this negative cosine phi is negative sine phi there. Alright, so if you do the determinant, because we have 0 nicely here, you can use the cofactor expansion of this one, or you can switch these two columns. So you have do the cofactor expansion on the first column, but sign switches. But if you do the honest calculation on this determinant of this one, it turns out that determinant is negative rho squared sine phi, not the positive. So if you parameterize in a different order, you can see that why not, putting phi first and then theta later, and what difference does it make? It's the same object and parameterize in a different order, and all that does is just switching the sign of this one, and our integral formula of change of variable, we always have this absolute value to avoid this problem. Okay, thank you so much. That was it.